Minor that was okay. Better turn up.
Yes.
So just tell me when you want to start, and I'll give you a little intro. Are there other there's a people who are going to come on the Zoom. Mark's there. Mark's there. Check you out. It's going to come. Oh, it's there.
Just testing things.
Oh,
Hello.
Maybe when I give you your introduction, you should mute just while I
Okay.
do that.
So thank you everybody for coming. I'd like to introduce Professor Parastoo Sadeghi from UNSW in Canberra, who is spending a week with us working on interesting things on information security. And today she is going to be telling us about offset symmetric Gaussians for differential privacy. So thank you very much, Parastoo.
So let me know. Okay, thank you everybody. So I'm gonna mostly be on the board and pointing to different things because I don't have a pointer. So I stop my video and then stand up. So that's gonna be the way. All right, so thank you very much. This is joint work with my co-author Mehdi from Swinburne University. And my work is supported by the ARC Future Fellowship. All right, so let's see, hopefully this works, yes. So just to sum up what we have done, the mechanism which we call offset-symmetric Gaussian is a hybrid between Laplace and Gaussian mechanism. So I will explain how that works. And it is mainly rooted in the Gaussian mechanism. So, and a bit of Laplace is somehow injected to it. Okay, excellent. Thank you very much.
Just the top button.
Yes, the top button. Yes. Okay, cool. So, so it's the good thing about it is it enjoys sub-Gaussian tail, so it can be good for reducing outliers and post-processing bias. And we can show that basically its privacy utility tuple is better than the Gaussian, somewhat between Laplace and Gaussian. So it is something that has a good tail performance like the Gaussian, but it can perform better in terms of the privacy utility pair. So just so I don't know, everybody knows here the background, but I just thought that maybe there are people online or just to say a few things, you know, this goes back to mid 1990s, but unfortunately this known that we can attack if we simply anonymize data sets, we can attack them very, very easily by linking what anonymous version of the data set is released to the public with some other health records of the same people. We can just cross correlate that and then get, you know, health records, financial records, whatever record that is being anonymized in quotation, we can just recover them exactly. And this is a well-known example. Unfortunately, still to the date, you know, some people might still be tempted to do that and remove name and, you know, date of birth, or remove some very obvious things, but then think that it is anonymous, but it is not. So a few slides are taken from a presentation by US Census Bureau, and this is very interesting because this was the method of choice for the US Census Bureau in previous releases of their census, where they aggregated or swapped data cells with each other to protect the identity of the people when they wanted to release the census results. So, for example, they, instead of individually saying with this household has this many people with this age and, you know, this kind of ethnic backgrounds or sex, they added them up and released the median of the age and mean of the age. But you see that there was no noise added, was swapping some household data in the neighborhood or aggregating them. But even this is a 2018 or 19 presentation. They use it on just like a off-the-shelf MacBook Pro with solving equations of what is the underlying data set. And it takes a fraction of a second to uncover exactly what was the composition of people that produce this table. So this is, they did this, they were trying to kind of question, you know, evaluate their own methods in the past to see what can be done better. They did another thing again from the same presentation. This is the result, that they reconstructed all the population, over 300 million records from the last census release, and then they cross-referenced it. They linked it with 4 commercial data sets, which included people's name, address, age, and sex. And then their reconstructed data sets from the census included ethnicity as race, which they said, let's call this the sensitive information, right? So this was the sensitive information. They cross-referenced what they reconstructed from census with commercial databases, and they were able to exactly recover 17% of population, their race and ethnicity. And basically this is this person with this age, sex, address, with this ethnicity and race, which they said this is not acceptable, which is amounts to about 50 million people. So it's a large, it's a huge risk. Then back in 2018, this is the front page of the slides that I showed you. They said that, okay, this method has been going for 12 years now, and it has been quite, popular. We are going to apply differential privacy for the release of the 2020 census data, and that was the motivation. They were going around and showing to people that their previous methods were no good, and therefore they need to do something different. So they said that this is the standard the framework we are going to use. After this, of course, you can imagine that differential privacy, I will talk about it later, but it's noise adding mechanism. So you add noise to the data. They have to satisfy certain statutory, law. By law, they have to report, it has huge implications in terms of the, voting districts, funding, government funding, federal funding, about the population of each district. It goes down to very low granularity up to the national level. This article was published in New York Times, where they the title of the article reads, I don't know whether you can see it, it says changes to the census could make small towns disappear. And these are quotations from that article, which says every person matters for federal funding. That's a fact. So that is absolutely true in everywhere, I guess. And then they add, their sentence was, imaginary people will be added to some locations and real people will be removed from others. And then minorities and rural areas are at most risk about when this kind of new technique is going to be employed. So and this is an area in near Arctic in Alaska, I believe. I'm not 100% sure, but I think that's Native American population. Oh,
we are still live online.
yes. Maybe it became overheated or something. Let me pause recording for a moment. Yeah, it became. Good, thank you. Okay, so what they did was that they took the 2020, they used some scientists to actually run this, you know, there were people who were analyzing what differential privacy means. What they did, I show you, I mean, this was a fairly technical article by New York Times where they showed, let me go back to here. They showed such graphs. I have selected, there were many more graphs, I think, but I selected 2 graphs to show you. What they had done was that they applied differential privacy to 2010 released output, treating it as the true, you know, they took the population counts in the 2010 results and applied differential Laplace noise to it. So this, let me explain what this means. The middle, this is logarithmic scale, both vertical and horizontal axis. The middle line is the true population as reported in the 2010 census, and this is logarithmic scale, whether if you apply noise, Laplace noise to it, whether you are over reporting by a factor of 248 or you are would be under reporting by a factor of 2.248. So this is counties, Black people in counties, so they were focusing on minorities and places. So the example that they highlighted in this article was that a population of 90 people was reported as 716. Well, maybe for that particular population, they were somewhat maybe happy because they were receiving more, you know, we need to build more roads, more funding, blah, blah, blah. But, you know, you can see that then other people, it increases unfairness. So there, for good reason, it made a lot of noise, you know, what this is going to do. And the other thing was that was reported is that when they applied the Laplace noise, a small and medium-sized reservations of Native Americans showed were underreported. So, and this is huge because they need funding to survive. They are almost entirely relying on federal and state funding. So this was concerning, and you know, and similar studies, I'm sure, was even, you know, there were court cases that, you know, in the state of Alabama, I think there were court cases about the use of differential privacy for census, you know. So I think that was interesting. The Australian Census Bureau is not using differential privacy, but they are interested. They have other perturbation. They have an adaptive, you know, interactive table builder. You can query the underlying data microdata of the ABS, and they have been used adding noise for many years, you know, to their results in a specific way. Actually, they have the same query results in the same count, you know, so they have a sticky type of noise that they add to the data, but they are interested in understanding their methodology from the lens of differential privacy, kind of what differential privacy levels are they able to provide with their perturbation method. And they refer to the US Census Bureau here. Of course, there is a community that they kind of look up to each other to see what everybody else is doing. So that is interesting. And essentially the crux of the problem comes down how to convince researchers, how to convince the public and politicians that we cannot rely on past methods. We have to do something. And how do we manage the trade-off? Even what is a trade-off for a lay person? Understanding that you cannot have everything, you know, you know, you have to do something about it, and there is a price to pay, but is sometimes hard to manage, and how to kind of convince people. So this slide is again taken from the same presentation. Not that I couldn't find the picture of a scale, but just because it was very important at the very high level. So that is that. And with that, I just hopefully can have provided enough motivation to go to the main part of the talk. So I just start with some basic, because in most census results, you know, if we take the census as an example, the query is a county counting query, you know, number of people of certain background, number of people living in a certain district and things like that. So if the true value of a count that we are interested is n, we add some noise to it, you know, and then we produce a noisy output. This is called the mechanism. So it's a noise adding mechanism where the probability that you report the count is I, given that the true count is n. If the noise is independent of the true count, which in many cases it is, then it just comes down to the probability of this noise being having the value of I minus n. So this is the basics, and the differential privacy is essentially for the counting queries. This is somehow gentler introduction. If we have the two databases X and X dash that differ in attribute of one individual, let's say one person smokes and in the other hypothetical data set the person doesn't smoke, the number of people who smoke is n versus n plus 1. So the differential privacy is where the ratio of reporting the same value I, given the data set there is n people in it having that attribute, or n plus 1 in it having that attribute, is somewhat small, thinking that if hopefully epsilon is a small value, this is bounded, this is in the ideal case, it is close, very close to 1. This e to the epsilon is a small, and therefore this ratio is close to 1, means that the effect of the person is indistinguishable. The effect of a person on the data output is fairly small. So that is the kind of, let's say, in terms of the counting query. This is the formal definition. I won't go into too much details of it, but essentially, again, the idea is neighboring data sets that differ in one element, one row, and then the probability that the output of the mechanism belongs to any set E, and for the X and X dash is essentially, you know, small. There is a nuisance here, like just a delta term, and this is something that we don't like to have, but sometimes is inevitable, and I will talk about it later. If we don't have this delta term, this is called pure differential privacy. So epsilon, think about epsilon being small, hopefully, and delta is some term that is kind of makes it a slack, because in some mechanisms we cannot have pure differential privacy, and of course, you know, we want to have this delta as small as possible. There is a lot of debate about what this means. There is some people want to interpret this as a probabilistic failure, but actually there is subtle differences between this delta, this additive term, and the probabilistic failure, and they are not quite equivalent. Actually, the probabilistic failure, if delta is small, there is no guarantee that the probability of differential privacy being violated is small too. So they are not, they don't mean each other. So, and the probabilistic the interpretation doesn't satisfy post-processing. So if you are interested, I can point you to an article about this. Going back to the Laplace mechanism. So Laplace, the pictures that I showed from New York Times, they were initially, Laplace was the candidate for the noise in the US Census Bureau. So if the sensitivity of the data set is delta, meaning that one person can change the query output by delta amount, and everything is additive, so you can, for the sake of argument, you can say one query is 0 and the other one is delta away from it. Essentially, you are adding this Laplace with mean 0 and mean that is shifted by delta. The ratio, the worst case ratio, determines that epsilon. And for Laplace, everything is nice and tidy because it's essentially an exponential based mechanism. It very well fits within the definition of this differential privacy, and in fact was the first one, the archetype, you know, mechanism that was proposed initially. So there is well-known, you know, relation how to choose the scale of the mechanism to satisfy epsilon differential privacy. Gaussian mechanism, you know, this does the same thing but with Gaussian distribution. Because it is going faster than, any linear, exponent here, there is no finite epsilon for which the ratio of these two probability density functions can be bounded by e to the epsilon. So the Gaussian is a very clear example where this slack parameter is definitely needed to make things work. And this is the way that the delta should be computed. So we have to find this worst case set E for which this ratio of these neighboring, mean shifted Gaussians is greater than e to the epsilon, and for sure it is a non-empty set. So this comes down to computing this set to find the delta. So just to summarize the pros and cons of Laplace. The pro is that, it is a golden standard in terms of having the pure differential privacy. It is easy to design because once we know epsilon and delta, the sensitivity of the query, we know how to scale delta, we know lambda, the scale of the distribution. It is proven, by Natasha and co-authors and ago that this is utility. It can provide utility, optimal utility in certain queries that that are monotonically, it generalizes some known results in the geometric case. For the discrete case, the problem with it is that it has the heavy tail. So the outlier was very specifically highlighted in the New York Times article, that you have this really 2 times, 4 times, even up to 8 times reported compared to the true population of a small county. Of course, the smaller, the bigger the noise will show itself, the smaller the population is. So these are the challenges. And we know that, Gaussian has good sub-Gaussian taste, so much less outliers and bias after post-processing. However, as I just mentioned, this delta factor is something that is bothersome. And how to compute delta, it is really not, I will scale it, I will zoom into this area, but essentially you have to compute the area under these two, the difference of these two curves when one goes under the other by a factor of e to the, when you have scaled it already. So this is, for example, for this particular numerical value, delta is computed as 10 to the minus 4 roughly. So this is the zoomed in version of that area, this tiny area between those two curves, and you need to compute the area under that. And for the Gaussian, it's very easy to compute, and this is where that crossover happens. So you have to compute every point from minus infinity to that point, and this of course depends on delta and the variance of the Gaussian and epsilon that you want to have. So that is about Gaussian. In fact, in 2021, they announced, in April 2021, they announced that they moved from US Census, they moved from discrete Laplace, which is a geometric distribution, to discrete Gaussian. Mainly, there is a recording, I can point you to it. They gave a presentation. In the presentation, the main reason they cite is the heavy tail of the Laplace and the outlier problem of the Laplace distribution or geometric distribution. And they say that they want to have delta much less smaller than 1 over the size of the population, the size of the data set that they are dealing with. In the US Census Bureau, they are targeting 10 to minus 11. So there is documentation about this, what epsilon is, how do they apportion it to different districts and localities up to the high level, up the national level. So our research question has been, can we keep the light tail of the Gaussian but improve on its differential privacy and variance tuple joint performance? And what we are showing here is that yes, it is possible to do that. And I try to motivate the distribution. That's why this offset-symmetric Gaussian is probably a good candidate to as something that both keeps the tail light, and also it has a better epsilon delta privacy performance compared to the Gaussian. So our initial gut feeling, you know, that's how it really started. I was playing around with, you know, the Gaussian, and I said, how about I modulate it? I somehow try to slow down, you know, the decay of the Gaussian, so that I can hopefully get a better epsilon delta. So it is not the product of two random variables, it's a pointwise product of the PDFs of the random variables, right? So it is just the product of a Gaussian with a Laplace with a parameter m. So you have sigma squared as the parameter and another parameter m that is the Laplace factor here. So a scale of the Laplace. So that was the original kind of gut feeling. And the other thing is that you have 2 degrees of freedom. In the Gaussian, you only have sigma squared, whereas here you have m, and you can hopefully play around with the relation of these things to design your mechanism a bit differently. This is one interpretation, that's how it is started, but the name of the offset symmetric Gaussian comes from the algebraic manipulation of this to see how it works. So if you basically write out the definition of absolute value here for positive, for negative and positive values of y, and then complete the squares by multiplying this term, which amounts to 1, and kind of factor out this will be your new normalization constant. And you see that you have one Gaussian when y is negative, and one Gaussian with another mean, but like symmetric mean on the other side when y is positive. So let's view this in next slide. It is essentially, this is the Gaussian at mean minus m, and this is the Gaussian at mean m. These are not part of the distribution, so that's why I have shown them with ... But you take the tails of these 2 distributions, and then you know the normalization somehow takes care of the area under it, which is this. I really like working with Q function. There are, you know, error function complement, all these sorts of things, but I like the notion of I use the notation Q notation. But essentially it is like that. So this is somehow in here, we will see that in here at the beginning, it behaves a bit more like Laplace, and then the tail is still under certain conditions, you can guarantee that the tail remains sub-Gaussian, as there is a sufficient condition for the tail to behave sub-Gaussian. So let me move. So this is also another good thing about it, because it's easy sampling. So if you know how to sample from a Gaussian or a discrete Gaussian, you can just reject the values in the middle and take the values that are in the tail and then shift them to the center, and you have your OSGT. So sometimes, you know, these numerical instabilities in finite computers may make you know, you have some maybe non-conventional distribution. If the sampling scheme is not, you know, really proof and watertight, you might lose this claimed privacy doesn't hold. So at least if it is at least based on some well-known, you know, distribution, there are many algorithms for it, and there is an algorithm in a paper for the discrete Gaussian. This can be done for the discrete Gaussian. The same rejection as resampling idea is working. So that is how you would sample it. And this is the interpretation, what happens when the value of the noise is small. When the value of the noise is much smaller than 2 times the input parameter, when you write it out, you can ignore this term in the summation. And essentially, when the value of y, when the noise is small, it behaves like Laplace, but then the tail is you kind of, as you see, that the tails are pointy, you know, when you bring them together, they are pointy, they are more like Laplace, and then they become Gaussian-like at the end. So this is a superposition of the distributions, Laplace, offset symmetric Gaussian and Gaussian at the same variance. So the variance of this much. I just want to point out, and I will talk about it a little bit later, these two are input parameters to the offset symmetric Gaussian. This is not its variance, and this is not its mean. It's of course a zero mean distribution because you have shifted everything to the center, the tails, and this is only the input, but the actual variance is much smaller. So the green one is Laplace, the red one is the Gaussian, and you see that it somehow nicely sits in between them at the beginning, and the tail is that this is a logarithmic scale in the vertical, so Laplace is linear in the logarithmic scale, whereas these two are decaying nonlinear in the logarithmic scale. So it is of course sitting in between. I mean, we are paying a little bit in terms of the tail. Tail is heavier, but it still decays nicely. In terms of the variance has a nice formula, easy analytical formula, easy to calculate, and it is easily proved that it is strictly smaller than the input value to the input parameter to the distribution. So this is sigma squared. The variance sits nicely below for small, for these values of m. And actually, as you increase m, it goes lower and lower and lower. But what we have proved in terms of its tail, this is a sufficient condition that we say that if the ratio of m over the kind of sigma, it's not the standard deviation of the distribution, but the sigma input sigma, if it is satisfying this relation, which is roughly 0.67, then you guarantee sub-Gaussian tail with respect to the original, with the input parameter. So at least it is sub-Gaussian with respect to a Gaussian with this kind of variance. So that is nice. And then with this, I like to talk about what is the privacy, differential privacy, utility, variance, performance of this mechanism. So we have to kind of start from first principles and try to evaluate. It is almost invisible here, but evaluate the area between these two curves. So it is not visible here. I show it in the next slide. But what I want to here show you as a one numerical example, at the same variance, we have compared the delta, for these particular numerical values. The delta of offset symmetric Gaussian is roughly an order of magnitude, is 5 times less than the delta for the Gaussian. So at the same epsilon. How do we? So this is a more extensive numerical results where this shows the delta as a function of epsilon. So this is the delta epsilon pairs that are achievable at the same variance. So we fix, these are again input parameters to the OSGT, but its variance, actual variance is equal to 27.7. We set the variance of the Gaussian to be the same, meaning that this is a proxy for utility. But essentially, we are adding less noise to the true query. So again, this is either at the same delta, you can say that you can achieve less epsilon, and the delta is really small. So we pick this value to be somehow relevant to the US Census Bureau values that they had delta 10 to minus 10. So you can have a better privacy measured by epsilon as is normally done. This is not only for one particular example. Pretty much whatever we do, it has different ends, different variances. We compare them at the same variance. Again, these two and these two are corresponding together, and you can see that again the delta epsilon pair is better. Then what we do is that you might ask, I want to have a certain epsilon and delta here, but I want to know what is the variance of the distribution. So I fix delta, for example, for 2 of these curves to be 10 to minus 8, and I plot what variance I need to add to the to the query to achieve this delta with any of these epsilon values. And you can see again that if you compare these two things or these two things, OSGT requires a smaller variance compared to the corresponding Gaussian distribution. So overall, the privacy utility proxied by variance is better. Overall, a better trade-off is achievable. We have some, I mean, I didn't show you the formula for it. We have a closed form solution for the delta. So the closed form solution has the difference of two Q functions. I only show you one of the cases, and it is a scale. You know, this scaling factor somehow turns up in the final result, and this can be shown that this is a decreasing function of sigma. Again, remember that sigma is the input parameter to the distribution. It is not the actual variance. If you want to compare delta for the OSGT with delta for the Gaussian, which is known in the literature, it only has this middle term. It doesn't have this term, and it doesn't have, you know, this. There are some nuances here, but if you forget those, you see that because this is decaying much, you know, more rapidly. This is a constant. M over sigma is a constant for a particular OSGT distribution. So comparing this middle part with this, and we know that this is a decreasing function of sigma. If you compare them at the same variance, this will be a much smaller quantity compared to the Gaussian distribution. So this is the kind of underlying analytical explanation of why we see those good results, and they are not just randomly, or we haven't selected them to be just this good. They are generally, because of that reason, they're better. I probably, how am I going with time? I probably try to wrap up in 10 minutes. Is that okay? So it will be 11:50, and we have some time for questions. So without going into the details, this can be easily extended to k-dimensional queries. You are not only asking about one particular count, but query, you have multiple queries that you want to ask from the database. So a k-dimensional query, again, the same idea is here, that you are essentially modulating a k-dimensional Gaussian with a k-dimensional Laplace. You are then it will be pointy in the center of the it will be a combination of L1 and L2 norm in the expression in the exponent. So again, you can see that this is variance for this achieving the same delta. I didn't present what delta is here, but for the fixed delta, these are the dimension of the query: 1 dimension, 3 dimensions, 5 dimensions. Again, the OSGT requires less variance to achieve the same epsilon delta pair. However, the improvement seems to be diminishing as the dimension goes up. So the good thing about OSGT is that it's kind of a soft if you have multiple dimensions, it's easy to go to Gaussian. You know, it's based on Gaussian. You can change M to be almost Gaussian. You know, if you have really high dimensions, choose Gaussian. I mean, we are not trying to sell it is for every possible situation, but there are many situations where this might be useful. There are lots of nuances, as I said, about delta. One other way to measure the privacy performances of mechanism is through the Rényi divergence. So this somehow, very broadly speaking, Rényi divergence of between two mechanisms at X and X dash is measuring how different they are without trying to add this kind of artificial delta value. It is really trying to say that what is the concentration of the privacy performance? What is the concentration of epsilon, so to speak? You know, how do we have a single bad mechanism where the privacy loss is infinity, or is it that everything is behaving more or less in a good manner? So without going into the details, you know, this is from the literature. This metric is from the literature, it has gained a lot of momentum, a lot of attention in recent years. That let's forget about delta. Let's look at this Rayleigh differential privacy. Let's look at this. What is the divergence of two mechanisms at neighboring data sets? We compute this, we can upper bound it very easily. There is a linear with alpha. Alpha is the order of the divergence, Rayleigh divergence. So there is a linear term with alpha, which depends on the sensitivity of the query and the input parameter, this sigma squared to the mechanism. And there is a zeta term here, which dies down as alpha increases, but actually it can be big when alpha is small. Gaussian Rayleigh divergence doesn't have this zeta term. It is alpha times the query sensitivity, and then it will have this 2. But you need to remember that you need to put in the variance, that if you want to compare them at the same variance, again, this is smaller than this green term. Therefore, the Rayleigh divergence of the Gaussian at the same variance is going to be bigger than and the bigger the worse, you know. So bigger means they are more separate, they are more distinct from each other, measured by divergence is distribution, so it is less private. So that is a very well-defined mathematical term in terms of the what it means actually. Then I don't want to go into any of these details, but we have the exact computation of it. That was a kind of a very loose upper bound. Here, this is a loose upper bound. This zeta term is a loose upper bound, but it's easy to compute. There is a not so easy, you know, it's a little more involved. It involves the Gaussian CDF, but anyway, you can compute this. I have the code I can, you know, share with you. It can. It is expressed like that. How can this be used if somebody is really stuck with the idea that they want to compute the delta performance, epsilon delta performance of this OSGT mechanism in composition, for example, if you are using the mechanism over multiple times, a gradient descent, you know, you are doing lots of iterations as you are applying, you know, noise, the privacy performance of the mechanism goes down. So you can use, well, this is applicable for Gaussian as well. So whatever you have computed as the Rayleigh divergence of the mechanism, you can, I will probably skip this, you can, if the Rayleigh divergence of your mechanism, whatever mechanism it is, this is general result and it is from the literature, but we just used it in composition and in noise filtering and things like that in the paper. If the Rayleigh divergence of the mechanism is smaller than or equal to tau, you can convert it to delta. So delta is a function of alpha, the order of divergence, and this tau and epsilon. You can then take the infimum over all alphas. This gives you the tightest delta that is possible if the divergence of the mechanism is tau. So you can convert this into, if the measure of privacy is epsilon delta, it is possible to use the moments accountant, it is called in the literature, to get the delta and then compare them, you know, how do they compose, and we have some results in our paper. I'm happy to discuss offline with you, but it's something that, you know, I don't think the level of details is suitable for this presentation. But this was published last month, I guess. It appeared in June, July. So you're more than welcome to look that up, and I'm happy to answer questions after this or by email later. So with that, I think I should stop. And sorry that I didn't use my basically pointer on the screen. So hopefully everything was clear for the audience over there as well. Okay, let me mute myself for this.
Thank you very much. Just give a clap. Thank you so much, Parastoo. That was a really great talk. Does anybody in the room or out of the room have a question for Parastoo?
I have a question. Oh, So have you used this in any applications?
What we have, so let me try to unmute myself. Okay, so the question was for people who didn't hear, was that have we used it in any application? Not directly, no. This is just introduction. There was a lot of math involved in order. It is different from Gaussian. It can, but the derivations were, we just try to introduce it and understand its basic differential privacy, utility, variance, and all that. So we haven't used it as application. By application here, I mean just basic. We only presented one post-processing of this, you know, how you might, because one of the reviewers actually asked us, what about if you apply some noise filtering, you can apply some signal processing linear filter at the output of the mechanism to try to reduce the noise, if you know, for example, that the distribution of the query is also Gaussian. So we just showed some results that even after filtering the improvements, you know, it does better in terms of filtering performance at the same privacy level. And we showed that the composition of this is also better than the Gaussian. So if you are, because Gaussian is very popular in gradient descent, what we showed here is that it can give you more iterations. You can do, if you want to have a final epsilon delta of, let's say, 10, let's say 10 and delta being 10 to minus 5, 6, you can run your gradient descent, you know, for 20 more iterations, let's say, because then your convergence, your performance in terms of the utility measured by how many iterations you can run is better for the OSGT at the same, you know, final privacy performance. So the results are in that. This is kind of indirect pointers that potentially it can be used in application. So we have composition results in the paper.
Yeah. So I guess the follow-up for that would be, I was wondering how efficient it would be to compute this, because you said you can do it with
Sample it or
rejection sampling.
yeah.
Rejection sampling. Do you know how it compares with the efficiency of computing a Gaussian?
Okay, so look, depends on M, you know, if you are waiting for these very unlikely events to happen, you have to wait for a long time. But what I showed here is that, you know, so it really depends on what I showed, as we usually use, if you want to maintain a good, because if in the limit, I mean, if you are really trying to do this tail, it goes very, very pointy. And that means that you have to wait for a very long time to get these tails. That is not and it becomes almost like a singular Laplace distribution. That's not the intention of this mechanism. The intention is to have M relatively small, a little bit. So the larger the M, the more pointy and Laplace-like it becomes. That is not the intention. So you need to have a kind of a moderate, small to moderate M, and M over sigma, basically, because this guarantees that the tail is behaving nicely. You are not getting a singular Laplace that is, in the end, I don't know what happens to it. This bound that we have is independent of M. That's the good thing about this. The second line is just shows that the tail, if M is less than that value, you know, the tail is behaving nicely with respect to the input parameter sigma squared, which is good enough, you know, for our purposes. And if M is not too big, your sampling hopefully is, compared to the standard deviation, you will hit those points. So 0.6 means that you are even less than a standard deviation from and definitely you will get those values. So it will be as good as, you know, it will not cause problems in the intended operational regime. Yeah.
We have a question from Mark Gatz.
Okay.
Online. Do you want to handle it?
Okay, let me have a look. Oh, but I can't see it.
Oh,
He's
okay.
about to speak, I believe.
All right.
Oh,
Okay, there is a hand. Yes. Yeah.
My camera. Sorry, the cat was walking over me. That was a really nice talk. Thanks very much.
Thank you.
So I was interested in we were talking about using it with gradient descent, and you mentioned the moments accounting approach.
Yes.
So I can kind of see how that fits, but I was wondering how much how complicated you thought it would be to incorporate what you've done into the moments accounting.
We are just using that, you know. So this moments accounting approach is already. Let me go to the final. Quickly go to the. The moments accounting approach has been worked out for a general mechanism, and the end result of it is as I have shown in this slide. I can point you to some papers that have done this, and it is really, you know, all you need to do is work out what is the Rayleigh divergence of your mechanism. And what we have shown here is that it can be worked out, and all you have to do is plug it in and do the, there may be some numerical stabilities, you know, there is a range that you can do this, but there are based on moment accountants, there are also some optimizations that have been done in the literature that is not necessarily on moments accountant, but they also, you know, in the end, they give you somewhat similar expressions. You know, this is very easy to compute. They have some optimization expressions. They are a little bit numerically unstable, but in the end, you can get, you know, you can try to get the tightest bound on delta, either based on moments accountant method, once you have worked out what is your Rayleigh divergence, and also, or based on some numerical optimization. The numerical optimization may be a little bit numerically unstable, but if you have some library that are really high precision, I have been able to do it, you know, in Python using some very high precision libraries. So overall, I'm using existing results in the literature. All I'm doing is computing my Rayleigh divergence.
I should have said, so my background's actually machine learning, and so I was interested in a deep learning kind of context where you use the moments accountant in a DP SGD kind of context. So I was wondering whether that was something that would be kind of complicated to extend your work to, or in fact, just because I was looking quickly through the transactions paper that you mentioned, and it didn't seem to mention, I mean, deep learning as a kind of motivation for possible work, but not an actual application to that yet. Oh, you're muted.
Yes, yeah. Yeah, we haven't done, I mean, it's a motivation for our work. We haven't really, you know, applied it in there, but I imagine that it can be used as a mechanism and for learning. Similar, wherever Gaussian is used, our guess is that it is applicable, and it can be leading to either more computations possible at the same privacy, or, you know, you can get better privacy for the same number of for the same learning algorithm, for the same number of iterations on both. But yeah, I haven't really, I'm not expert in that. So it was just mainly to motivate it. Thank you. So let me see.
Do we have any more questions? It's probably nearly on the hour, right?
Yeah.
So what I can say is that you're still around for another couple of days, yeah?
Until Friday.
Okay, great. So if anybody has questions for
until Friday,
Parastoo,
yes.
and she's on level 2,
Yeah.
so giving away your privacy.
Email me. I'm happy to even have a offline, set up a Zoom, or if you are not on campus. But yeah, thanks very much for your attention.
Thank you very much. Let's give Parastoo one more clap. And thank you. Do you want to stop the recording?